Okay, so I have the honor to introduce our next speaker, Mark Schwartz. He's an assistant professor at the University of Minnesota, the College of Veterinary Medicine, working with the Swine Group and the Swine Disease Eradication Center. He has been a great contributor to the industry, so I just want to highlight some of the areas he's worked with our industry. So he's been the board member and president of the Swine Health Information Center, and he currently serves on the Minnesota Port Board. So he's also worked in the Animal Health Task Force, and he's been heavily involved in the U.S. Swine Health Improvement Plan. So just had the honor to introduce Mark. His presentation is going to be Beyond P-Values, Embracing Complexity in Animal Science Inference.
Thank you, David. Good afternoon. It's a pleasure to be here today to visit on this topic. I promised Pedro that I'd make this topic as exciting and dynamic as possible on the interpretation of p-values. And how this came about is we planned this session. We talked about the limitations of gathering data and conducting field trials, and the difficulties, and even doing that and doing that correctly is if we in fact met the assumptions and we've collected our samples randomly and we have independence, et cetera, is interpreting the outcome. And so, and I've been through, many meetings which we review research trials, and we put a value to each statistically significant outcome, whether it's growth rate or feed conversion or mortality, carcass yield, et cetera, or we perhaps may give a value times that difference to a trending p-value, or we may do any difference, that's numerical difference. And so in that, again, it's understanding how to work toward not over-interpreting outcomes and understanding that is field data. And even in a controlled study, we have to be very cautious. And the spreadsheet I made some years ago to help people understand this is how this presentation came about. So we'll talk about is something called the golden sentence, and then just what is a p-value? What is the definition, or I should say, what are the definitions of p-value? And then understanding how we move from a test statistic to a p-value, with the exception of the Fisher exact test for that, and limitations, what this outcome or what this value does not tell us. We'll go through a number of misperceptions, because it's very common to hear these as you work through data with groups in the field. And then a spreadsheet I made to help explain this and maybe portray why we have to be cautious in our interpretation. As I prepared for this, I spent a lot of time. I had to dig out 4 or 5 of my statistics and biostatistics and spatial analysis of epidemiology, infectious diseases, which is very statistics heavy. And I'm sure there's multiple people here in the room that have much more qualified than I, but I worked to put this together for a diverse audience. And to start out, to really understand what we're talking about is a quote that I took from actually an online instructor that my daughters used, or I pointed them to when they're in AP statistics in high school, and a very dynamic teacher. They said, really, this is what we're trying to explain when we talk about inference, right? I was curious about a population parameter. However, a census was not reasonable, right? It's either impossible, impractical, or unethical, right? In the case of human medicine or trials, et cetera. So instead, I took a sample, and I used the data to calculate a statistic, and I used that statistic to make an inference about the population parameter. And that's what we're doing when we're doing trials. We're making inferences about the population. We're not making inferences about our statistic. We know that, right? And that population parameter, remember, whether that's a mean or whatever it may be, is an unknown value. We're making inferences about where we might think our mean is, and if we think it's reasonable that that population mean is somewhere near our sample statistic. So we saw them all morning, and I just grabbed some randomly selected studies, and we see it all the time, right? We see the p-values stated. This study was of iron and an attribute or characteristic in nursery. Coincidentally, from Dr. Johnson, this one was zinc, and I'm part of this group, as is Pedro. And again, we report our outcomes in p-values, and this one randomly uses the subscript and defines significance as less than 0.06 for some reason. And so we see it all the time. We see it in our data in the field when we're going to go to that level of statistical analysis. There's multiple tests that yield a p-value. We'll talk a bit on the t-test today just to keep it confined to that discussion. And again, whether you're looking at the difference of two sample means, whether you're looking at the proportion of two different samples, and a chi-square, right, for looking for association or goodness of fit. There's binomial and negative binomial. And in spatial statistics, we still yield a p-value on these on spatial data. There's a p-value yielded from Shapiro-Wilk will tell us, or we can make inferences if our data is normally distributed. And using that assumption so it's kind of a circular type of analysis there. So there's very specific assumptions under which we're working on parametric tests. So one of the definitions I pulled out of one of my textbooks was a definition of the p-value. And the p-value is the probability of getting values of the test statistic as extreme as or more extreme than that observed if the null hypothesis is true. So we're working under this hypothesis that we are working under the assumption that the null hypothesis is true. And so hypothesis testing, we're always saying, okay, I have some statistic, right? Some sample statistic, and let's say it's the difference in means of the end of the nursery weights of pigs. And our null hypothesis is that this difference is 0, and the alternative is that it is not 0. It's some value not equal to 0. And from there, we're working under our null model. In this case, we'd have a normal distribution, our mean being 0 of the population, again, unknown where that is in the population, and what is the likelihood that our finding would contradict the plausibility of that difference being 0 in our sample relative to the population. Second definition is a p-value is the probability of observing data at least as favorable to the alternative hypothesis as our current data set if the null were true. And so again, we go from test statistic to p-value in all tests, to my knowledge, with the exception of Fisher exact test, which yields the p-value directly. In the t-test, we're looking at sample means, variance, and sample size. Chi-square is observed versus expected, either a test for goodness of fit or for association. T-test, or F-test, looking at the variance, the ratio of variances from the within to among groups. Moran's I looks at clustering and spatial data. Kuzik-Edwards and spatial clustering of case controls. So just examples. And then from the old days, you look in a table and find your test statistic score, and from there look at your range of p-values given that test statistic. So again, we go from this test statistic. We'll talk about the t-test. And so that formula there is very important. It shows you intuitively you have some test statistic value, right? And we're going to use this 2, which is very common, which is about 2 standard deviations from the mean, right? That's this, gives us this 5% alpha level. And as the sample difference in this sample means is larger or greater. We have a larger t-value, t-statistic, therefore it will drive us away from the mean. As the variance increases in the denominator, we'll get a smaller t-value, and as the sample size increases, we get a larger t-value. So those factors, and you can think about that intuitively, how that each of those. If a very small sample size, it'll be very difficult to get a value, a t-value very great. If your mean differences are very, very small, again, unlikely to get a large value. So then we have this t-distribution and this rejection region that we've talked, and we commonly, this alpha of 0.05 is saying that we're really, it's going back to saying, we're saying that this observation is so unlikely if the null were true because it's approximately 2 standard deviations from the mean. I think it's easier for me intuitively to think about this from a spatial aspect. We're saying, whether the probability of observing some pattern could be due to chance. Right? We can see that spatially, I can anyway. And it's hard to see that in a data set, but this is saying, does the statistic seem to say that the pattern is inconsistent with it being from a random distribution? That's whether we're doing that with spatial data, with observations in a study, et cetera. So one thing I think is important, and I find interesting, is that we have this rejection region and the type 1 error, type 2 error, and the alpha 05. If you go back to one of the fathers of statistics, R.A. Fisher, in 1926, in his work, and to quote him, he said, "Personally, the writer prefers to set a low standard of significance at the 5% point." It's going to equate to about 2 standard deviations from the mean. A scientific fact should be regarded as experimentally established only if properly designed experiment studies rarely fails to give this level of significance. And so what he's implying is that the p-value less than 0.05, that one should repeat the experiment, not to take that as the outcome and to not question the outcome with one finding. And the interpretation of significance would say it's, in his opinion, worthy of notice or meriting more experimentation. And so, again, in the field level, I think it's very important. I think many of us here have talked to 2 different vendors of whatever you want to choose, whether it's genetics or feed, and you will find that this sire line beat this one, and then it was reversed and reversed. Why? That's my point. We have to know that the conditions under which the studies were conducted vary, and there's differences in if actually we've met the assumptions of the normality, et cetera. So limitations of p-value. So we have this clear definition, right? We talked about that several times, this observed result, but what does it mean? Because we get a p-value 0.05 or less, but it tells us nothing about the magnitude, the effect size. Doesn't tell us where that range of how likely it is to be far from that value. Because we don't know the sample size, the sample size will drive that value, and I'll show that in a bit. So that's one of the limitations of the p-value. The misinterpretations of p-value, it's interesting, a survey I found in the Uppsala Journal of Medical Sciences, a survey taken asking 75 doctoral students and 64 statisticians, does a statistically significant t-result of 0.024 allow for inference as proof or probability statements about the truth or falsehood of the null and the alternative? So 10% of statisticians and a quarter of the students said it means that the null is not true, and about half or more said it was improbable, when the correct answer is you cannot draw any inferences about the truth or falsehood. It's only a measure of the hypothesis probability. So 10% answered correctly. My question, as we talk about this topic, if this is representative sample of the population of statisticians, or happen to be outliers who answered the survey. So some of the misperceptions of the p-value, I take this from the work of Goodman from 2008, and most of these misperceptions. The first one, if p is equal to 0.05, the null hypothesis has only a 5% chance of being true. No. The p-value is calculated under the assumption that the null is true. And again, go back to that definition. And so this statement is one that is incorrect. Secondly, a non-significant difference, so p-value greater than 0.05, indicates there is no difference between the groups. Again, no, it's statistically compatible with the observed results. And any non-significant p-value less than 1 is less consistent with the null than equal to 1. I think about this as I look at enrolling pigs, for example, into a study in the field, and I'll look at the numbers and say my p-value is 0.4, and so that they're from the same population. They're not, it's not a 1. There's some difference. This is important too. A statistically significant finding indicates clinical, commercial, or economic significance. It does not. We have no idea of the magnitude of that difference. An overpowered study could have a very, very small difference between the two means, for example, and have a very significant p-value far less than 0.05. This one, trials of outcomes of greater than or less than 0.05 are in conflict with each other. No, because the trials could have identical effect, but differing p-values due to different sample sizes or variance. And so this, I just did a hypothetical mean of 54.7 and 52.8, so about 2 pounds. Again, an imaginary, hypothetical end of nursery weight for some trial, for example. Another one with about the same difference in mean. The difference is sample size of 8 versus 100. A p-value of 0.2, we'd say is not significant. Nothing going on, nothing interesting. The other one, a p-value of 6 digits to the left of 0, highly significant. The sample size is the driver of that. Another one, trials with the same p-value provide the same evidence against the null. Now, different effects can have the same p-value. Both these would be reported as p-value less than 0.001. The trial on the left, the hypothetical data set I created, difference of about just under 2 pounds. On the right, less than a 5 pound difference versus a 2 pound difference. So we don't understand, we don't know from the p-value the effect size. Another one is p-values are properly expressed as inequalities only if it's less than 0.001. Otherwise, we would sure want to understand, given the limitations even, if a p-value is 0.049 or 0.01 or 0.02, etc. We'd want to know that value less than 5. This is one not in Goodman, but one I threw in. For example, p-values derived from a trial is 0.33. This indicates the treatment results in an effect 1/3 of the time. No. Again, go back to the definition. It has nothing to do with when or the effect size or effect frequency. So the confidence interval is a step up from the p-value in that it's derived from the same equation, but it gives us an interval estimate versus just this point estimate. But we can do that again intuitively. We know that a confidence interval encompassing 0, for example, and a difference of means, if it encompasses 0, the p-value is greater than 5. If it does not, it would be less than 5. We can do that intuitively. And so again, as you look at the equations of how those are derived, it's using the sample size and variation and the difference in means. And so again, an example on the left, I have a 54-pound mean as a hypothetical data set versus 52 with standard deviations quite similar. On the right, the same difference in means. Sample size of 100 versus 1,000. On the left, I have a non-significant 95% confidence interval. On the right, I have highly significant, I would call it, a 1 to a 2.8 pound confidence, or 95% confident that, again, to interpret the 95% confidence interval, it's not saying in this interval we're 95% sure that the true population mean. We're saying if we did this study over and over and over and sampled and sampled and sampled and had 100 confidence intervals, 95 of those about would contain the true population mean for the difference in means. That's the interpretation of that. So p-value results with a hypothetical data set, this is where this kind of started from. In using this to show people the caveats of interpretation. Again, we have to be sure that our study design is adequate. We're meeting these very specific assumptions of normality and variance and et cetera. And is our sample representative of the population? Was our collection randomized? Are there any confounding factors? Is our sample size adequate, et cetera? So what this is this is a hypothetical. Again, I created a column of values called TX for treatment and a column control. And those are 100 observations under each of those. You just can't see the bottom 70 some. And it would appear to be normal distribution, kind of. My standard deviations are 9.9 and 7.3, so that would meet that criteria. And so given this mean treatment value of my sample of 52.8 pounds in this hypothetical test, this may be a sire line trial, it may be a feed additive, it may be a vaccination protocol, et cetera. And my control is 50.14, so I have roughly a 2.7 pound difference, and my p-value is 0.027. And we're going to say, whatever we're doing, we're going to switch to this. There's a significant difference here, and we have a sample size of 100, and 30 is my magic number, apparently, in statistics. But we have the green values with the asterisk. We're going to change that value of 78 in the treatment just by random chance, and we're going to change those two in the control from those values. And we're going to change all those from a 78 and 2 at 36 to 55. And it wasn't why we weren't biasing it. We just randomly happened to choose a pig in our randomization method. And my p-value goes from 0.027 to 0.077 with 3 changes out of 200 total observations. And now we would say it's trending, and we're not so sure if there's a difference here. And now we're going to change one more value in the another pig in the control that just happens to be 55 pounds compared to 39. And we're not even trending now, we're 0.115. And we'll say it's not significant, and this difference is due to random chance. And so I like to show this to people that we understand the concept and the value of repetition and replication, of studies, and that we're truly randomizing our sample groups and when we're doing our studies. So again, to summarize very briefly, p-value is derived from a test statistic, one of many different that can be utilized depending on the data set you're working with. Typically, we're making inferences about the population parameter, almost always from our sample, spatial analysis being the exception. Very important to remember that significance does not equal magnitude. There's no association of, because it's a low p-value, that difference is of value to us. The misperceptions we covered, the interpretation under 0.05, and then how these trials could have different outcomes with the same p-value or different outcomes with the same effect. We always have to go back to our definition of the p-value and to remember that what we are doing, if we could use a census, we would not be talking about any of this. We would know those values. We're doing this because we are not able to do a census. We have to rely on our sample to draw inferences about our population. With that, thank you very much, and I can take any questions.
Questions for our speaker? Yes, Dr. Lee.
Mark, when you talk about misperceptions and problems, one of the problems I see quite often is the experimental unit. Could you make some comments on the experimental unit and defining that, or what that is and how to use that, and how that might influence your results?
Exactly. Is the pig in a pen a unit? Is the entire pen a unit in the study is a litter, the unit of study. And again, so if we're drawing inferences about the sample, and it, to draw inferences at the pig level when really the unit is the litter, for example, correct? Yeah, and so that's, I didn't even pull out my design books, I just stuck to the p-value books, but that would be another caveat, correct?
I'm just going to say thank you for making me realize how much I've forgotten about statistics and p-values, Mark.
You're welcome.
Okay, let's thank our speaker, Mark, one more time. And with this, we have 15 minutes of a break. We'll come back at 2:15 with the next two speakers. Thank you.